This video illustrates the use of DataShop to perform exploratory analysis of geometry tutor data, generate a theory for optimizing a cognitive model, and test that theory both visually and statistically within DataShop. It also illustrates more broadly how educational technology data can be used to gain insights into student thinking and learning. We start this analysis by exploring learning curves of knowledge components for the dataset Geometry Area 1996-1997. One of the things we notice is that we have some nice learning curves for skills like circle area. The error rate's high and then goes down, and similarly for pentagon area and trapezoid. Parallelogram area is low and stays low, so there's not much learning there, but there's also no need for learning, so it's not too worrisome. One curve that's a little bit odd, however, is the composed by addition curve, because you can see that it's flat here, and there doesn't seem to be any learning going on. You might also wonder, what is composed by addition? So that's one reason to go look at these problems and see how they're coded. We also want to become familiar with the domain a little bit, and see what the tutor problems look like to students who worked on them. This POGS problem is an example of one of the problems that students saw, and when they see it in the tutor, these first three columns are initially present. Given the radius of the POG and the size of the square, they're asked how many square inches of the scrap metal are remaining, so they have to find that. Of course, the way to find that is to find the area of the square and the area of the circle, and subtract the two, but they don't have to do it in their head. They can add columns, and put the area of the square and the area of the POG there. Here the student adds a column for area of the square. Then she adds a column for the area of the POG. These columns are optional in the tutor. Students don't have to enter them. There are some problems, like building a sidewalk, where similar things are going on. Here they need to find the area of a sidewalk by finding the area of the swimming pool and the area of this larger rectangle, the yard, and then subtract. But in this problem, the key columns that you have to subtract, area of the pool and area of the yard, are already present in the beginning, so the student doesn't have to so much think of setting those as sub-goals. They are there in the first place. It turns out that in the original cognitive model, finding the area of the sidewalk, this kind of subtraction of that additive structure, and the subtraction in the POGS problem were treated the same. They're both part whole structure, and the skill in that original model is called composed by addition. We can hypothesize here that maybe the composed by addition curve isn't going down, because in fact, there are different kinds of composition and the harder one. Maybe what's causing these blips here is an increase in those kinds of problems where you have to come up with the sub-goals yourself, as opposed to being given them. We need to figure out which of these problems containing composed by addition actually require a mental decomposition because the columns weren't there, and which of them didn't. We know that POGS requires the mental composition, so we might call that knowledge component decompose. The sidewalk problem will stay as composed by addition. There are a few other problems that I've looked up and determined whether or not they also require this mental composition. We'll now implement the new knowledge component model in a format DataShop can read. Then we'll import it into DataShop. We first need to export the existing knowledge component model, or KC model, called textbook new. Opening this KC model in Excel, we want to zero in on just those composed by addition rows, and particularly the problems that we care about. The first thing we do is turn the auto filter on. Now we see a list of our 10 KCs. We just want to look at composed by addition rows, so I deselect all and just select composed by addition. Now we see a limited number of problems here. Some of them, like building a sidewalk, are going to remain as composed by addition, while some of them, like POGS, we're going to change to decompose. In the existing columns here, I enter the KCs for the new KC model. I can make changes to the existing column because DataShop will prompt me to rename the KC model when I import it. Now let's look at a statistical measure of goodness of fit for the new model. We see lower AIC and BIC values for our new model compared to textbook new, which indicates that the model with the extra knowledge component better fits the data. In this original model, not only is it flat, but the error rate is substantial at points, starting at 27%, almost 30. Here it is 50% at 12 opportunities, which is still 24 students. Not a small piece of the sample, as opposed to out here where there is just one student with an error rate of 100%. Here we can apply a feature of DataShop to filter out data points for students who had more than some number of opportunities with this case C. We'll use this opportunity cutoff and set the maximum number of opportunities to 20. This eliminates data for all students who had more than 20 opportunities to use this knowledge component. Now let's switch to our new model for this KC, which will renumber the x-axis opportunity. Remember those peaks we saw before, like that 50%? It's pretty much taken out here. Everything is below 30%. This new model shows the smoothing of the learning curve. We can further smooth it by setting the max opportunity cutoff to 12. For a student, it's probably not the subtraction of those two areas that's hard. Just because the columns are given to you doesn't mean you know which ones to subtract. But you at least don't have to think, oh, I need to figure out the areas of these two. What's the formula for a circle? That's a complex process that the previously overly general KC requires that this one doesn't. This one at least requires you to think, which two numbers do I need to use, and what do I need to do with them? Subtract. Now I have to do the subtraction. A 20% error rate is probably much more accurate for what this piece of the puzzle is, whereas the other piece is much harder. Let's take a look at our new KC, decompose. It's a bit noisy. We don't have a lot of data, so the number of observations here is somewhat limited, but it looks pretty reasonable that there is real improvement. I'll set the maximum number of opportunities to 10. That looks better, but the curve is still pretty bumpy. Further investigation led to hypothesizing a new knowledge component, and using that model further yields a better fit. If we set the secondary KC model to this new model, decompose arith, we see that the latest model tracks the decomposed KC even better. In this video, we hypothesized a new knowledge component based on an unusual learning curve and explored that hypothesis in DataShop. We started by looking at a flat learning curve for a knowledge component, examined the problems that students saw containing that knowledge component, and hypothesized that the original knowledge component was too general, covering two dissimilar cases. We split the knowledge component into two, creating a new knowledge component model, and imported it into DataShop, where we discovered it better fit the data both statistically and visually. Our analysis also revealed some new insights into student thinking and learning.